So ingredients of our lectures, first lectures, will be as follows. We start with notion of a vector bundle. I believe you know about them a little bit from lectures of Professor Troitsky. Yes? Maybe, okay. Next question which we will discuss the connections on vector bundles. So specific differential geometrical notion, connection on a vector bundle. And after that we pass to title of our course. We will discuss characteristic classes. The theory of characteristic classes is very huge, very huge. And our approach will be based on differential geometry. And it has special title, Chern-Weil theorem. It means the following thing. You have a vector bundle and you write a specific differential form which represent characteristic classes. Well, after that we discuss differential operators. Where? So differential operator should act on something. Usually differential operator acts on functions. But in this setting, differential operator will act on sections of vector bundles. And among those things, we are interested only in one very specific type of operators. Dirac type differential operators. Because index theory can be developed for very huge class of operators, so-called pseudo-differential operators. It's too much for us. We need to restrict ourselves to differential operators. And among those things, we still restrict ourselves to very specific operators, Dirac type operators, because these things are sufficient for us. They are sufficient for geometry. They are sufficient for physics. And the proof of Atiyah-Zinger theorem it has some different ways to state it. So there is k-theoretical statement, local statement, cosmological statement, blah, blah. There are many ways to state this theorem. We will discuss two of them, local setting and setting in theory of characteristic classes. I hope we will have time and we will, I hope, I don't know how it goes in the future, but we should spend some time on discussion of proof. Proof is difficult, but there is some short proof. It uses so-called heat kernel. It gives us a local statement of this theorem, but I don't know. I hope to discuss it. But I do not know if we have time, if you have ability to do that, but nevertheless, we will try. We will try. And in this thing, let me write it, local formula and some classic formulas. Namely, Gauss-Bonnet theorem, Hirzebruch, and some other statements. So this is very important thing from the point of view of differential geometry, because manifolds usually have some specific characteristics. For example, they have Euler characteristic, signature, A hat genus, and some other numbers. And all these numbers can be calculated by application of Atiyah-Zenger theorem to some very specific operator. Usually this is Dirac type operator. So this is why this theorem is important for geometry, for topology. It's also important physics and so on. So this is our plan. Okay, so now we start. We will start more or less slowly. We are not supposed to rush. So today we need to understand what is a vector bundle and learn some specific examples.
So a space that is locally diffeomorphic to a cross Cartesian product between some bases, and we have a total
Okay,
space.
so that's okay. So what we have? So let us fix field. Either real numbers or complex numbers, because we have two classes of vector bundles. Both of them are very important for us: real vector bundles and complex vector numbers, complex vector bundles. So if everything I will tell you will be valid for both types of fields. Okay, so we fix field. So we fix fiber. Usually it will be denoted either by vector space V, or maybe I will write something like k to the power of r. So r-dimensional vector space. What is difference between this notation and this notation? Very simple. If I write V, it means that I don't want to pay attention for specific bases in this space. If I write this thing, then I know that in this space some basis is fixed. Okay. So, in informal way, we understand vector bundle as a collection of vector spaces, of r-dimensional vector spaces, parameterized, we discuss smooth case. So in a smooth way, we will give a specific statement. What does it mean? By points of some manifold. So we have a bunch of vector spaces, and they are in some sense glued one to another. And the parameterizing point belongs to some manifold. Some very specific, two examples. What I wrote here. I wrote collection of one-dimensional vector spaces, yes? Each line which I wrote here is R1, etc. What is the parameterizing space in this case?
S1.
A circle, yes, because you go along, each vector space corresponds to some point, yes? You take a point and you go along this bundle, and you see that after you go around, you return to the initial point. So this is a vector bundle, vector spaces, parameterized by S1. I will write you another example. draw. I will not write, I will draw it. So this is a Möbius band. But this Möbius band represents a collection of vector spaces. In which way? In this way. Each line which I draw here is R1. Situation is the same. It is a collection of one-dimensional vector spaces parameterized by points of what? Points of circle. Because you go along this middle line, you go around, return to the initial point. This is also vector bundle over S1. So this is two pictures you should have in mind. One of them is trivial, another one is not trivial. Trivial one is direct product. We will give an exact definition in a minute. And here you see non-trivial vector bundle. Then you go along parameterizing space, you see that fibers are twisted. So you went around this middle line and then you return to initial point, the fiber flips around 0. So now let us give exact definitions. So idea is okay, yes? Okay. So you don't need to think it's one-dimensional. I can draw you another picture. So for example, this is a parameterizing space B, and for each point x you have specific fiber EX. So this is you can think that it's a plane, another plane, yet another plane. But obviously this is not a way to discuss this subject, because we want to draw some formulas. We're just saying blah blah blah. This is a picture 1, picture 2, picture, but we need to write the formulas, because Atiyah-Zinger theorem is a very difficult formula on the left-hand side and also difficult formula on the right-hand side. So we need to write some formulas. Let us pass to this thing. How to speak about formulas. Trivial vector bundle. Very simple thing. You have total space, which is direct product of base by your vector space V, and also it is projected to the base by P. That projection is given by very simple formula. What do you think about that? How you think about that? You think about that as a direct product. So this is a base, this is a direct product of base in horizontal direction and fiber in the vertical direction. No problem. So if you want to look at fibers, what are the collection of vector spaces? This is a collection of vector spaces. No twists, no some tricky things. It is just trivial vector bundle. And now we define object, which is most important for us. Locally trivial vector bundle, as you told us. So we speak about vector bundle, locally trivial. This is a very important thing. Locally trivial vector bundle of rank R, and we say over field K. So K could be real numbers or complex numbers. So this, what you have to describe if you want to speak about locally trivial vector bundle, you need to have a collection of the following data. So total space. So you should think about that as a union of all fibers. Also you have base. This is a space which parameterizes fibers. you should have a projection. So if you have points which belongs to some fiber, then you should to know which point corresponds to this fiber in space of parameters. Almost all, but not at all. So also you should have trivializing charts and local trivializations. Let me write it in this way. So alpha belongs to some index in set A. So this is a collection of data of all things you need to know to discuss the vector bundle. Because we speak about locally trivial vector bundle, so let us speak about what we have here. E and B should be smooth manifolds. Is it possible to consider not manifolds, some other spaces? It's possible, but in our setting, because we speak about differential geometry, we want to consider only smooth manifolds. Pi from E to B is a smooth surjection. Each fiber, what is a fiber? So you take point in the base and you consider the following subset, EX, EX, which is part of the space E which sits over point X. You should think about it as it is drawn here. This is E, this is base B, this is point X, and projection gives you so collection of points which projects to X. This is EX. Is a dimensional vector space over the field K. And now we want to explain what does it mean that these fibers are glued together in a smooth way, and the operation is also glued together in a smooth way, because you can think that, look here, we have two fibers, one and another. Here we have some structure of vector space, and here also we have structure of vector space. Who knows if these structures are close to another if we consider fibers which are close one to another? Nobody knows. That's why we use local trivialization. Let me write the most important part of the definition here. Well, here we write that U alpha is an open cover of B. So it means that each U alpha is open and union of all U alphas is B. Well, the most interesting thing in this definition is psi alpha. What is psi alpha? For every element of our open cover, if you restrict your projection to preimage of the open set U alpha, so you can think about it as a P minus 1 of U alpha. So this is a part of our vector bundle. So you can think about it in the following way. So this is base, this is total space, and this is not very big part of our B, which is U alpha. And the points which are projected to U alpha under projection pi gives you a part of E. This is E alpha. E restriction to U alpha. This is just part of total space. So we require that this part of total space is trivial vector bundle. And more or less, moreover, we fix this trivialization. So we require that, this is part of structure, psi alpha. Here we have direct product with k to the power of r. Here is projection to u alpha. And this is a projection to the first element, because if you take a point in this direct product, you can project it just to the first point. So x v goes to x. And this local trivial, psi alpha is a local trivialization. And we require that it on each fiber, it is a linear isomorphism. So this is a way to explain why structure of the vector space varies in a smooth way than you go around base. So this is a definition. We need example. Please tell me some example. Very difficult question. What is an example of locally trivial vector bundle? Yes, the most simple example of locally trivial vector bundle is trivial vector bundle. This thing is example of a locally trivial vector bundle. Very good. Okay. Before we proceed with some other examples, let us introduce a very important notion of gluing cocycle. Are you acquainted with it? Gluing cocycle. Yes. Okay, so let me remind you what is the gluing cocycle. Imagine we have two local trivialization which intersects at some place. So we have u alpha and u beta, and their intersection is not empty. For simplicity, I will write this open set in this way, the same as write it in this way. I will write, the order of letters has no meaning here because you can interchange the order here. So I will not pay attention in which order I write these letters. If you look at the part of the total space which sits over this intersection, then you can trivialize it in one way and by another way. What do I mean? First of all, the trivialization psi alpha is defined here. Then you write u alpha beta cross k to the power of r, and this is a projection to the first term. No problem. But since this is a part of u beta, then you can trivialize this part of total space in another way. You can apply here psi beta and obtain another representation of this thing as a direct product. Both of these representations preserve projections, they preserve linear structure, blah, blah, blah. So everything here is fiber-wise isomorphisms. But you have this commutative diagram. Imagine you pass from this direct product to that direct product by composition of the following form: psi alpha minus 1, inverse diffeomorphism, and then with composition with psi beta. What can we say about that? It takes point xv to some other point yw. let us discuss what is relation between these four objects. So first of all, I fix that x and y belongs to u alpha beta, and v and w belongs to kr. What can we say about the relation between these points? In a very general sense, because I have defined nothing more, so this should be something very, very general.
Why is it called Cocycle?
There is no Cocycle yet. It's just we want to define transition functions. They should appear. It's not yet defined. So this is just, we consider this diffeomorphism, which preserves fibers, preserves linear structure, blah, 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 because this thing is diffeomorphism preserving fibers and preserving vector spaces, yes, and this also has the same property. We take this composition, so we pass from this space to that space, preserving structure of direct products, structure of linear spaces, and so on. So the question is, what can we say about relation between these four letters in a very, very general sense? We cannot prove some theorem. We just should say this coincides with that, maybe. I don't know. What would you suggest?
X and Y are equal.
Yes. X and Y are the same because this diagram commutes with projections. So letter X goes to letter X here, letter X goes to letter X here, and if you pass from this product here, the first letters in these things should project to the same place. So X should be equal to Y. Very good. What can we say about relation between letters V and W?
Linear transformation.
Yes. If letter V goes along vector space k to the power of r, letter W also goes along this letter. So it means that, and I require that this thing should be fiber-wise isomorphism, and each fiber is isomorphism. That means that W depends on letter V in a very specific way. G is an automorphism of k to the power of r. Or if you prefer, it is general linear group over field K. It consists of matrices R by R. Invertible matrices R by R. Very good. That's correct. But I want to say that this G is not just G. We need to write that it depends on something. Obviously, at different points of this space, this G should be different. G depends on X. Because who knows, at one point you write one isomorphism. In a close point you write some other isomorphism, maybe close to the initial one, but different one. Okay, so a correct way of writing this formula is as follows. So this was some explanation, some hints, blah, 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 but the correct formula is as follows. Psi beta, composition with psi alpha to the power of -1 of xv has the following form. First argument, x, is the same. Second argument is transformed but in a linear way, g of x applied to v. And here, I should write an index which explains that you consider this composition from alpha to beta. Yes, so we write here beta alpha. So let me introduce you this thing. Okay, my question is G beta alpha, what is it? From mathematical point of view, how we should understand this object? Matrix. Yes, that's correct. It's matrix, but it's point-dependent matrix. If you change point x, this matrix also changes. We will see some examples in which this matrix changes. And actually, we should think about it as a function which is defined on the intersection u beta alpha to GL. How I wrote it? GL. Here we wrote field, here we wrote the rank of matrix. So it's a function which goes, so on the intersections of trivializing charts, we have transition functions. These are transition functions. In the nearest future, we will see very interesting thing, that in some cases, value of this G beta alpha could be smaller than general linear group. It can be smaller because you know that in general linear group we have very interesting subgroups. Very important one. So we could, G can take values in smaller groups. For example, unitary, special unitary, orthogonal, special orthogonal. What other cases could you imagine? Symplectic, great, symplectic. Okay. Not our case, but let us symplectic. There is very important example. Then the group is bigger than this one. Spin or complex spin. These two groups are bigger than general linear groups, so you know twofold covering. But that's why we need to discuss it in details later. But remember that in some sense, in some cases, we will see vector bundles with bigger structure group. So you heard the name, structure group. So if all transition functions take values in some specific group different from that, so you say that G is structure group. So if all transition functions take value in orthogonal group, then you say that structure group of the vector bundle is reduced to orthogonal group. If it is here, so you said that you reduce structure group to the unitary group. We will see that in all cases, then you speak about real vector bundle, you can reduce structure group to orthogonal, but not always to special orthogonal. It depends on orientability. You can reduce structure group to unitary in all cases, and so on. So for a while, we should stop this discussion of structure group. Now I want to ask you, okay, I wrote this formula, so I defined transition functions G beta alpha. You asked me what is a gluing cocycle. Where is cocycle? Very simple thing. We know that these functions should satisfy some specific conditions. I believe that Evgeny Vadimovich told you what are the conditions. Could you tell me, please?
It's like G beta alpha, G alpha theta, and G theta something. And then you contract like you.
Okay.
G alpha beta,
The composition.
G beta alpha equal to.
Yes, a very simple case. Then you write U alpha alpha. So is it possible that you can take the same U beta as U alpha? Who can forbid you? Nobody? So you can write transition functions, G alpha alpha of x, it should be identity. You did nothing. You didn't pass from you passed from one trivialization to the same trivialization, so you did nothing. So your matrix should be a unit, identity matrix. If you have non-empty intersection and you have transition function G beta alpha x, but you can go in inverse direction and consider transition function U beta alpha. What do you think about relation between these two things? It should be inverse, because one is you go from left to the right, and then you go from right to the left, and both of them are linear isomorphisms. We know that this is invertible matrix, and this is also invertible matrix. No problem. And now we write, so now the Cocycle condition appears. This is an answer to a question. So if you take triple intersection which is non-empty, so U alpha beta gamma which is non-empty, then you, on intersection, you can consider three matrices, G beta alpha, G gamma beta, and you can consider product of these two matrices. What you obtain? G gamma alpha. It's obvious. If you think about it in an informal way, that should be obvious, because what is written here? You pass from trivialization alpha to trivialization beta. Then you pass from trivialization beta to trivialization gamma. Why you need to pass through trivialization beta? Go straight from alpha to gamma. But obviously you need to prove it. You need to write a formula and to check that it's correct, but it's more or less obvious. Maybe you want to write the same formula in this way. G alpha beta, G beta gamma, this product of matrices, G gamma alpha, this will be identity.
The same one.
The same, absolutely the same. But maybe people who like cocycles say this is cocycle or this is not a cocycle, because this is a boundary condition in some complex. Okay, so this is a notion of gluing cocycle. Very good. So now we see that if we have a vector bundle, we can construct gluing cocycle. What does it mean? It means that we have functions G alpha beta from U alpha beta to specific group G, such that, let me write this condition as star. So if we have vector bundle, we can define gluing cocycle. Gluing cocycle is collection of functions such that these conditions are satisfied. Okay, did I wrote a definition of gluing cocycle or not? In mathematics, if somebody says something, it is either definition, either theorem, either proof or example, or some blah blah blah. So the question is, did I give you definition of gluing cocycle or not?
Definition, you need to have if and only if for a definition. Always need to. When you define something, it's only if and only if. Right?
Yes, okay, but
Here I don't see if and only if.
oh yeah, well, yes, he's correct, because I didn't give you a definition. Because what I did, I constructed something, yes, and said that it satisfies some properties. There is no definition. I just said, okay, I constructed some object. Now let me give you a definition. Actually, it is written, already written. So, Cocycle with values in a group G. So this G can be any group, but we will discuss the case and G is linear group, GL, or orthogonal or unitary, something like that. So we take a space B and open cover. Its open cover. So before speaking about gluing Cocycle, I need to have a manifold and its open cover. Then I say that function for every alpha and beta such U alpha beta is non-empty. I need to have a function G beta alpha from U alpha beta to the group G, such that property that those conditions are satisfied. So assume we have manifold, open cover, and functions such that conditions which are written here are satisfied. Then we say, then this collection of functions is a gluing Cocycle. I would say with respect to open cover. So now I gave you a definition. So now we see the following thing. We have vector bundle, then we can construct gluing Cocycle. Let me be more precise. I wrote here group G, but actually I should wrote group GLK of R. Yes? Because actually my Cocycle takes values in non-abstract group and very specific, general linear group. Please correct it in your notes. The question, is it possible to pass in reverse way? If I have a Cocycle, could I construct a vector bundle or not? Usually if teachers ask, so yes or not? Yes, yes, it's possible. In some sense, you can ask the following question. Is it possible, so imagine you had the vector bundle and you constructed gluing Cocycle. Then you forget about the vector bundle. Is it possible to restore the vector bundle? Okay, it's possible. I will describe you how to do it. Other way, so assume you have gluing Cocycle and you don't know that this gluing Cocycle arrived as something defined by vector bundle. So some initial way, we start from gluing Cocycle. Is it possible to construct a vector bundle? It's possible. We will construct vector bundle with the same gluing Cocycle, and this will be your first exercise. I will describe you how to construct the space. So what we do, let's assume we are given B is manifold, open cover U alpha, and gluing Cocycle G beta alpha for this open cover. Gluing Cocycle with values in general linear group. I don't want to consider orthogonal, unitary, doesn't. this would be a non-necessary detail. So let us think that values are in general linear group. Now we construct the total space. Consider space X, which looks like disjoint union. Disjoint union means that pieces which I write here are non-intersecting. U alpha cross k to the power of r. For example, if you have, well, are you comfortable with this disjoint union? I don't know, I'm just asking. I'm curious.
Yes.
Okay. So we have pieces. That's too much because we know that these pieces should be identified in some way. For example, well, imagine you have B, and this is one trivialization, and this one is another trivialization. If you look to the space X, it consists of two big pieces. So this is U1, this is U2. This is U1, disjoint union with U2. So you see that in this union some points should be identified. Let me write how to identify them. Projection from X to B is defined in a very simple way. So you take X, which belongs to U alpha, vector V, which belongs to KR, so this pair projects to point X. The problem is the same point X can be seen, can be represented by a point in some other element of the open cover, because X can belong to U alpha and U beta. And the identification is given as follows. So we say that E is X quotient by equivalence relation, which is given in the following way. X V, which belongs to U alpha cross KR, is equivalent to point YW, which belongs to U beta cross KR. So I should write something if and only if. And the operator forbids me to write there. So I should erase somewhere. Okay, I'll erase here. Okay. Now I want you to tell me what is equivalence relation. So point XV, which belongs to this thing, should be equivalent to the point YW in this direct product. If and only if. Tell me, please.
And the gluing cocycle related.
Gluing cocycle relations are satisfied. Everything is okay.
Yes, and if V equal to G something, this G times W.
It's the second statement. You should give something, give some conditions which you need to have to write this formula.
Yes, the conditions.
Two conditions. You said second condition.
Yes, the first X equal
Ah,
to
okay,
Y.
okay, very good. So both of you told true. Okay. We need to know that alpha and beta intersect in non-empty way, and X is equal to Y, and they belong to this intersection. And then we say that vector W is represented by application of linear operator from gluing cocycle applied to V. That's all. I will give you some problems to solve. Quite simple. But nevertheless, check that E is a smooth manifold. Please find the dimension of E. Second, we see that there is a projection, because projection pi, which is defined on X, is compatible with these equivalence relations, so we have projection here. Please write trivializing charts. Trivializing charts and corresponding gluing Cocycle. Well, is it the same as the Cocycle we have in the beginning of our construction? So we have Cocycle, we construct vector bundle. If we have vector bundle, we can trivialize it and look for new gluing Cocycle. The question is, will this gluing Cocycle coincide with initial one or not? Just check. It's not very good thing for us because we're just writing some letters. We do not consider examples. It's very bad. So, exercise number 3 is as follows. Please tell me what is the simplest vector bundle in geometry. Not very simple, but what is the very simplest? Tangent bundle, yes. So, for tangent bundle and cotangent bundle, please write trivializing charts and gluing Cocycle. I want to see exact formulas, okay? Trivializing charts and gluing Cocycle. I believe that you know everything from these exercises, so we don't need to go into details. And now we pass to one very important question, very important example. It's true that this is a simple case, but there is so-called tautological line bundle. Over projective space so we write it in P field, and here is dimension. This is a projective space over field K, the projective space of dimension R. Maybe the more usual way to write it is real projective space, or CPR. You can meet in the literature this notation, that notation, and also this notation. Maybe in literature more related to algebraic geometry you will see this one. Well, the idea is as follows. There is a very specific line bundle, very important in our setting, over each projective space. I will consider real case. The notation for this thing is gamma. Sometimes people write gamma 1 just to know that it is a one-dimensional, so line bundle. Or sometimes people write gamma 1 over field K. I will write just gamma, maybe gamma 1, I don't know. From time to time I will write this one or that one. So let me describe it, this line bundle. Before we proceed, tell me please, what is a projective space? You already know it. What is projective space?
These lines.
You have an equivalent relation. If two points are by one factor, then
Okay. So what you start with, so we speak about real case. Complex case will be the same. I just want to write concrete formulas. So we start with points which belong to Rn plus 1. Yes, and we say that point x0, xn, and we omit 0. We don't allow all these numbers to be 0. Is equivalent to point lambda x0, lambda x1, lambda xn. Is a real number and lambda is not 0. So we impose equivalence relation on points in the space Rn plus 1 minus 0. In geometrical sense, it's just a line which passed from 0. All these points, equivalence class, is just a line which passed from 0. That's why people sometimes say that real projective space of dimension n is just space of lines in space Rn plus 1. If you are very, if it's quite simple for you to think about two lines which pass from the origin and say, okay, this is 2 points between in some space, that's okay. Very good. So we obtain our Pn. Now I want to say you what is the total space of this line bundle. Let us consider Rn cross Rn plus 1. Tell me please, what can we think about this object? It's a trivial vector bundle over projective space. It's direct product, it's trivial one. But it is big enough to have inside it gamma. Gamma sits inside, and it consists of, so a point in Rpn is a line, yes? Line which passes from 0. And also we have a vector. Now I imply condition. So condition is V belongs to the line L. That's all. So space gamma, so the fiber of gamma over point here consists of all vectors which belongs to this line. If you say it if you say this in words, you should say the following. The fiber of this gamma over point here consists of all vectors which belongs to this line. For example, I will draw you a picture for gamma over Rp1. Okay? Tell me please, what is Rp1? One-dimensional projective space. It's a projective line. Yes, from topological point of view, just as one. Yes? So we can think about it. So this maybe, okay, so say this point is included, this point is not included, because if you go under this axis, you will repeat the points. Okay? So this is a fiber over x. X is here. Oh, well, okay, P. So this is a point of my projective space. It is represented by line. And then I say, okay, vectors which belongs to this line forms a fiber of this gamma. It's geometrical description. And what I want you to do, as a problem number 4, most difficult one, to write trivializing charts for the projective for gamma. I want to see trivializing charts for gamma, but I don't want to consider too many letters for gamma over RP2. It will be far enough, RP2. And doing Cocycle. So we need some tool to write trivializations, blah blah blah, to relate geometrical imagination with formulas, and this tool will be needed for you to solve the problem number 4. Without it, I do not met in previous time any person who can solve this problem without understanding what is a section. Let me explain you what is a section. Section of a vector bundle is a map S from base to E, total space. Okay, it's smooth. Everything we consider is smooth. All spaces are manifolds, all maps are smooth. I will not mention it anymore. Then we will see an exception, I will tell you about it. Such that this composition is identity on B. So you take section, you go from base to the total space and then project it back, then you should arrive to the same point. Roughly speaking, you should have in mind the following picture. You take point X, you see the fiber, and you choose value S at the point X only in this subset, only here. Not here, not there, just in the fiber. And the section can be very strange. It varies along. If you move point along base, the section could be of any form. With the only exception, value of the section at the point X should belong to the fiber of the point X. This is written here. Let us fix it. S of X belongs to the fiber over point X. This is a notion of section. Everybody knows at least one section of any vector bundle. Which one? No, vector field is difficult. Who knows if you have vector field or not? Vector field is for tangent bundle. Now I see I took some vector bundle, and my question is: everybody knows what is everybody knows at least one example of a section. Yes, zero section, because zero section. S of X is just 0, which belongs to the fiber of the point X. Sometimes people use zero section to identify base with very specific subspace in the total space. You can think that, so imagine this is a base, this is a fiber, and then you move along base, this fiber rotates, and if you go around base, some loop maybe, so this fiber comes back to the same fiber but with some twist. If you look at Möbius band, you see what happens. Then I wrote Möbius band. I didn't draw the space B. There was no projection. You remember it? Then I draw Möbius band. There were no projection. I just wrote Möbius band. Then I wrote middle curve. It was a circle. and then I draw fibers. Yes? So this picture was about representation of the base as a zero section of the vector bundle, because there were no base drawn, if you remember. I draw only total space, and the base was embedded into the total space as a zero section. Okay, so zero section always exists, but I don't want to speak about zero section. I want to speak about very specific collection of sections. So, local section. It is a section which is defined only on some open subset. Namely, imagine you have U inside B. Local section over U is a map from U to E with the same property. P composition with S gives you identity, but only on U, because it is defined only on the point of U. If you look at the picture, you will see the following thing. This is B, this is E, this is part of base, it's open set U, and your section is defined not globally, not over all base, only on this part. But the property is the same. For point X, S of X belongs to the fiber over point X. Why we need local sections? Because we want to give the following definition. Basis of local sections over open set U. What is it? It's collection of sections S1 blah 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 SR. The dimension of fiber is R. That's why we have exactly R sections. All of them are defined over U, and they're sections of the total space E. The condition such that for any point X which belongs to U, vectors S1 of X, SR of X form a basis in vector space EX. Okay? Okay, let us discuss why we need to speak about local section. Why we do not speak about global section. Well, before we we write a couple of formulas, then we draw a couple of pictures. Okay, so just to finish, we will draw some pictures. I want to say that trivialization over U is the same as a choice of the basis of local sections has very specific name, local frame. This thing is called local frame. I also want to use this notion as a choice of a local frame. Let me explain you why. So then you have trivialization. You do the following. You take a piece of total space which projects directly to the open set U, And then you have diffeomorphism of this subspace, submanifold, to very specific manifold, which has this form. It's direct product of U with vector space. But remember, this is not just a vector space. This vector space with chosen basis, because this is written as, in a way, R to the power of K. And now I want to show you how to pass from trivialization to a local frame. Everybody can tell me. Trivialization, local frame. So imagine we already have trivialization. Would you suggest me some sections of this trivial vector bundle? S1, for example, I can send X to where? I need to choose a vector in the fiber over point X. Which one?
Can choose the first vector.
Yeah, yes. But not here. Here. Because this is a part of our vector bundle. This is just representation of this piece in the direct product. So I take a point X and send it to the point X, comma 1, 0, blah, 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 0. So this is the first basis vector in this space. But it sits here, and I want it to be here. That's why I need to have trivialization. Psi to the power of -1 of this object. So this is a section, it's genuine, honest section. Okay, S2 sends X where? Psi -1, X, comma 0, 1, 0, blah, blah, blah. How many sections I can write in this way? R. Let me omit the details. So if you have trivialization, then you can construct a local frame in the moment, no problem. Okay, if I have a local frame, how to construct trivialization? How to do it? So I have collection of sections, S1, blah, 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 SR, and they are linearly independent at each point. And I want to write representation in that way. It's interesting, but much more simple is to write psi -1, inverse. So imagine you have a point X and a vector in this space, R to the power of K. So you have a collection of numbers, A1, AR. Now I need to find a point in the total space. How to write the point? Very simple. You just write a sum of what? AJ times section at the point X. And you take a sum from 1 to R. S, J are vectors which sits in one fiber. You take these vectors, linear combination of these vectors with this coefficient, and then you obtain arbitrary point in the fiber. Changing A's, you will obtain all points in the fiber. Okay, you can say why you need to prove something, that something is smooth, something is continuous, everything is okay. We will skip it for a while because there are some difficult constructions, so just believe me that everything works here. Okay. Because there are some hidden cliffs and some problems. Everything is clear. Okay, so this notion of local frame you will need to use, then you will write trivialization for the tautological bundle. Without a local frame, it will be difficult to understand what you are writing. Okay? So, now example. Let me ask you how you will trivialize tangent bundle to a circle. We know that this is a trivial. How to trivialize tangent bundle to the circle? It's trivial, obvious. It's trivial, believe me. How to trivialize tangent bundle to the circle? Either you need to write it as a direct product, or you need to give me global frame. So if the vector bundle is trivial, then it has global frame. Local frame. Sorry, louder.
Vector with norm equals 1.
It's not an answer because every vector can be normalized to have norm 1. You have something different in mind. There is, you don't need to impose any relation on norms here, just you need to linear independence. What is the rank of this vector bundle? 1. So we need to have one vector which is a basis. So we need non-zero section. Okay, non-zero section of tangent bundle to the circle. You can draw it. Yes. This is a circle. This is a collection of tangent lines, yes? Okay, so I choose vector which looks here. So you go along circle in this direction, so you write velocity. This is a section. If you want to write a formula, I will give you the formula. Look here. Phi is the coordinate. Angle is angle. Yes, phi is an angle.
We need to solve two action.
Sorry?
For trivialized.
Which action?
Group action of SO2.
Well, not necessary. This is quite stupid case. This is an explanation because it's Lie group, and Lie group also always have trivial tangent bundle. But if we speak about some precise answer. So this is a coordinate, and the vector which is tangent to this thing is very simple, d over d phi. This is a tangent vector. This is drawn here. If you want to represent a circle as a collection of complex numbers, it's also possible to, if you write S1 as a collection of complex numbers which are equal to 1 after taking modulus, then section at the point z. So what is a section of at the point z? You need to have a vector which is tangent to the circle at the point z and is non-zero.
Can multiply by e?
Yes, sure. Because here you just rotate this in this direction by pi over 5. This is a global section of this one-dimensional vector bundle. No problem. Okay? Let me ask you some more difficult question. Everybody knows that SU2 is the same as S3 as differentiable manifold. Yes? That means that three-dimensional sphere has trivial tangent bundle. We already said it. If it's Lie group, then tangent bundle is trivial. You take a local frame at the unit and then by left translations move it at any other point. So this is it. Okay. But if I want to look at the trivialization in geometrical way, how to do it? There are at least two ways to see it. So we have a point x, y, z, and t. I want to see 3 sections which are non-zero and are linearly independent in each point. I will give you one vector, for example, minus y, x, minus t, z. This is the first section. You see, if you take a scalar product of these 2 vectors, you will obtain 0. So this vector belongs to the tangent space in this point. Clear? Okay. But it's not enough, because this is 3-dimensional. Tangent bundle has rank 3. I need to have 3 sections. This will be your exercise number 5. Find S2 and S3. And check that this is a local frame. It is a local frame. Well, this is a direct proof, direct question, and exercise number 6, exercise number 6. Then we spoke about circle. Actually, we have 3 ways of thinking. 3 ways of thinking. Okay, well, maybe x, y, and the section is equal to minus y, x, yes? Minus x, minus y, x, yes. We thought about it as a Lie group, this exact formula, this geometrical way, and also we thought about it as a complex numbers, yes? So here, we look here in geometrical way, just giving exact formula for tangent vector, but we need 2 more tangent vectors such that they form a local frame at each point. Why I wrote here local frame? It's global frame. We want to trivialize this thing globally, global frame. Well, exercise number 6. What we know about numbers, except real numbers and complex numbers? Something like numbers, but not complex and not real. Yes, quaternions, H. Yes? Apply your knowledge about quaternions to trivialize tangent bundle to S3. Use quaternions to trivialize tangent bundle to 3-dimensional sphere. I think it's enough for first lecture. You have 6 problems. On Friday, we will meet, and I hope you will explain me how to solve these problems. Okay? The most important for us is the problem about trivializing tautological line bundle. Well, that's all. Thank you.